Good morning, students. Dear students, as in the previous video, we had discussed about the apparent weight of a man inside the lift, and we had solved the numerical based on that in that video. Till the topic, that is apparent weight of a man in the lift, Newton's third law of motion, second law of motion, and first law of motion we had already discussed. Now, today, these topics are for this year's syllabus only for recapitulation or revision. So, we had revised in this chapter up to Newton's third law of motion, apparent weight of man inside a lift. Now, today we will discuss the part 7 of the video lecture on the chapter 5, that is law of motion. And now today we will discuss about law of conservation of momentum. So, first of all, we discuss conservation of momentum. Conservation of momentum. We will discuss about conservation of momentum. Now, what is the meaning of conservation of momentum? So, conservation, as you know that Newton's second law says that force is directly proportional to the rate of change of momentum. So, according to Newton's second law, Newton's second law, force is directly proportional to the rate of change of momentum. And according to Newton's third law, action is equal to negative of action is equal to negative of reaction. So the conservation of momentum is the combination of these two laws. It is the conservation of momentum is the consequence of the result of these two laws. So conservation of momentum consists of conservation of momentum as the combination of Newton's second law, so it is called as consequence of the result of these two laws, that is Newton's second law and Newton's third law. So what is the statement for conservation of momentum? So we will first discuss about the statement for conservation of momentum. And the statement for conservation of momentum shows that in the absence of external force, in the absence of external force, the net momentum of the isolated system remains constant or conserved. In the absence of external force, the total momentum or net momentum of the system remains constant or conserved, and it does not changes with time. Or you can say that the total momentum of an isolated system of interacting particle, or you can say that if F external is equal to 0, then total momentum of an isolated system remains now. Here you are seeing that again and again I am saying about the isolated system. Here also we have discussed about the isolated system. Then what is the meaning of the isolated system? What is the meaning of isolated system? So let us discuss about the isolated system. Then we will proceed for the proof of conservation of momentum. Proof of conservation of momentum when the system of particle in a system, the net force on the system of the particle in a system is 0 or no external force is acting on the system of particle. So first we discuss about isolated system. Isolated system. What is the meaning of isolated system? So if we suppose a big body, and this big body consists of two particles. Suppose this is particle A and this is particle B. Then when particle A and particle B, when particle A and particle B are interacting with each other, then the force exerted by particle A on particle B, let us suppose this force is FBA. Force on particle B due to particle A, and the force on particle A due to particle B is FA. FBA is equal to force on particle B due to particle A, and FAB force on particle A due to particle. This is two forces, and what you are observing here, that you are observing that FAB and FBA are of opposite nature but equal in magnitude, are of opposite nature but equal in magnitude. So this is called as isolated system, and so we can write it as FAB is equal to minus of FBA, and you can say that FAB plus FBA is equal to G. FAB plus FBA is equal to 0. So internal forces, this can be considered as internal forces. Suppose this is body of mass m. So if it is a body of mass m, then these are the internal forces. So internal forces cancels each other and does not play any role in conservation of momentum. these internal forces does not play any role in the conservation of momentum, or they does not affect the momentum of the system. This internal. So here I just want to say that these internal forces does not have any role. Means when we are talking about the conservation of momentum for a body of mass m, then there is a question in your mind, sir. If there is a body of mass m, then the particles of which that mass m body is constituted, they are interacting with each other. They are interacting with each other inside the body. So their interaction, that is the internal forces inside the body of mass m, is considered as zero, and they does not play any role in the conservation of momentum for a body of mass m. So if we are talking about the conservation of momentum of the body of mass m, then we only concentrate over the external force which is acting on the body of mass m. So this is all about the concept of internal forces. Now we go through the proof for conservation of moment. Proof for conservation of moment. Proof for conservation of moment. We talked about the proof for conservation of momentum. For this, we will consider two particle system M1 and M2. We had supposed M1 as a particle system and M2 as the particle system. Both has masses M1 and M2, and the momentum for particle M1 is P1, and the momentum of particle, initial momentum of the particle M2 is P2. So we have considered M1 and M2 are two isolated particle system, and the initial momentum for particle of mass M1 is P1, and initial momentum of particle M2 is P2. In such a way that total momentum of this system of particle means I have taken an isolated system, and M1 and M2 are the two constituent particles of that isolated system. The momentum of M1 is P1 and the momentum of M2 is P2. So total momentum P is equal to what? P1 plus P2. P1 plus P2 is the total momentum. Now, what we are doing? We are applying a force F1. We are applying a force F1 on mass M1 and F2 on mass M2. If external force F1 and F2 is applied on masses M1 and M2 for time delta, for a small time interval delta t, if we are applying the forces F1 and F2 on masses M1 and M2, then what will happen? Since the force we had applied on masses M1 and M2, due to that force the velocity of both the particles is going to be changed, and if the velocity of the particle M1 and M2 is going to be changed, then it is obvious that the momentum of the particle also changes. So for application of the forces F1 and F2 on masses M1 and M2 for a small time interval delta t, it produces change in momentum delta P1 and delta P2. It produces change in momentum delta p1 and delta, it produces change in momentum delta p1 and delta p2. So net change in momentum, net change in momentum. Initially it has momentum p1, p2, but we had applied force F1 and F2 on mass M1 and M2 for time interval delta t. So due to the application of force F1 and F2, the momentum of the particle changes to delta p1 and delta p2. So net change in momentum by after application of force F1 and F2. Net change in momentum, it can be written as delta p, and it is equal to delta p1 plus delta. Now del p upon del t is equal to delta p1 upon delta t1 plus delta p2 upon delta t2. And as we had discussed that for delta t tends to 0, or delta t tends to 0, if delta t, we consider delta t or change in time is very small, that is delta t tends to 0, then the change becomes very small. And if the change becomes infinitesimally small, very small, then delta p upon delta t can be considered as dp upon dt. So it can be written as dp upon dt is equal to dp1 upon dt plus dp2 upon dt. Now from Newton's second law, dp upon dt can be considered as dp upon dt can be considered as F1 and F2. Now dear students, look at here. From Newton's second law, rate of change of momentum is directly proportional to the applied force. And since we have to prove about the law of conservation of momentum, so the left hand side dp upon dt remain as it is, and we are writing dp1 upon dt plus dp2 upon dt as f1 plus f2. So from Newton's second law, dp upon dt is equal to f1 plus f2. dp upon dt is equal to f1 plus f2. Now F1 can be written as, I am breaking the force F1 into two parts, that is external force and internal force. So F1 can be written as F1 external plus F1 internal, and F2 is equal to F2 external plus F2 internal. F1 external, F2 external. So we can write it as dp upon dt is equal to F1 external plus F1 internal plus F2 external plus F2 internal. And further we can write it as F1 external plus F2 external plus F1 internal plus F2 internal. This is equal to dP upon, this is equal to dP upon dt. This is equal to dP upon dt. Now dear students, here, look at here. There are two bodies. If these are the part of an isolated system, then for this isolated system, if this is F1 internal and this is F2 internal, then we can say that F1 internal, as we had discussed it before also, F1 internal is equal to minus of F2. This is body 1 and this is body 2. F2 internal. So F1 internal can be replaced with minus of F2 internal. So we can write it as dP upon dt is equal to F1 external plus F2 external, and F1 internal can be replaced with minus F2 internal plus F2 internal, and it will cancel it out and it becomes 0, and dP upon dt is equal to F1 external plus F2 external, or you can write it as dP upon dt is equal to F external. dP upon dt is equal to F external. Then if F external is equal to 0, we have calculated that F external is equal to rate of change of momentum dP upon dt. Now if F external that is equal to 0, if F external is equal to 0, then dP upon dt that is equal to dP upon dt is equal to 0. And student, you are knowing that this dP upon dt is what? dP upon dt is the net momentum of the isolated system. P is the net momentum of the isolated system, which we have written as P1 plus P2. So if dP upon dt is equal to 0, then you are knowing that the differentiation of a constant quantity is equal to 0. Means here, if dP upon dt is 0, means if external force acting on the body is 0, if there is no external force acting on the body, then net momentum of the body remains conserved. P net is equal to constant or conserved. P net is equal to constant or conserved. P net, and in this way we have proved the law of conservation of linear momentum, that internal forces does not play any role. So we can say that conservation of momentum holds true if F external is equal to 0, it does not depend on internal forces. So here we can say that I am running on this piece. So dear students, we can say from here that if f external is equal to 0 for an isolated system, then its net momentum remains constant and internal forces does not play any, whatever the internal forces acting on the system does not play any role, and if the external forces acting on the body is 0, then its momentum remains conserved. Two examples I am taking for explanation of this. The first example is the bullet gun system. First example is bullet gun system. Bullet gun system. Bullet gun system. Suppose we have taken a gun and the bullet. We have suppose this is a gun and it fires a bullet. When we trigger the horse of the gun, it fires a bullet. This is gun and this is bullet. So for when we had fired the gun, when we had applied the force on the trigger of the gun, then the force is applied on the bullet and the bullet starts moving, and the force is F delta T. As the bullet starts moving, then the gun recoils with minus of F delta T. Minus of F delta T. That is the change in momentum of the gun and change in momentum of the bullet. F delta T. Change in momentum of bullet and minus F delta T. So the change in momentum of change in momentum of gun. F delta T is the change in momentum of the bullet and minus F delta T, then bullet gun system is initially at rest, so change in momentum of the system is 0. So change in momentum of the system is 0. That is momentum of bullet plus momentum of gun is equal to 0 throughout the motion, throughout initially and after that also, because they are treated as the internal forces. These are the internal forces and they are going to cancel each other. So the momentum conserved. Momentum always conserved. Second example is that, let us suppose there is a bomb. Let us suppose it is a bomb and the bomb explodes. If the bomb explodes and it breaks into two fragments, and both the fragments are moving in opposite direction. Both the fragments are moving in opposite direction with same velocity. Opposite direction with both the particles of the bomb is moving in opposite direction with the same velocity. Then it is considered as the internal force and the net momentum of the system. Net momentum of the system is conserved. Net momentum of the system is, in this case also, the net momentum of the system is conserved while explosion of bomb. Now we will discuss two questions, two numericals based on the conservation of momentum. Dear students, we have to show that Newton's third law of motion is contained in Newton's second law of motion, and for this again we are taking two particle systems. Suppose this is A and this is B. The force exerted by A on B is FBA, and the force exerted on B by A, that is FBA, A by B, that is FBA, and B by A, that is FAB. The FBA, force action exerted by A on B. Force action exerted by A on B, and FAB, force reaction exerted by B on A. These are the forces which are exerted on A. Now, from Newton's second law, you know that from Newton's second law, we can say that F is equal to dP upon dt. F is equal to dP upon dt. So FAB is equal to dPB upon dt, because FAB is the force exerted by A on B, means the force is going to be applied on B, that is the force of action. This is the force of action. So FAB can be written in the form of, by Newton's second law, dPB upon dt, and FAB, that is the reaction. FAB is equal to dPA upon dt. FAB dPB upon dt and dPA upon dt. Now, combining both the forces for the calculation of net force, F is equal to FAB plus FBA plus FAB, and it can be written as dPA upon, this is the, it can be written as dPB upon dt plus dTA upon dt and you can write it as d upon dt PA plus PB, and you can say that without any external force the rate of change of momentum of the whole system is equal to g. Look at here. This FBA and FAB are the internal forces. So, without any external force, by the law of conservation of momentum, you can write it as d upon dt PA plus PB is equal to 0, and you can write it as PA plus PB is equal to constant. PA plus PB is equal to constant or conserved, and dPA plus dPP can be written as, or if you are not writing, you have applied on the basis of this, so you can write it as dPA plus dPP as FBA plus FA, because from here also you have find this value from here. So you can write it as FAB is equal to minus of FB, or you can say that action is equal to negative of reaction, means this is Newton's power. This is nothing, this is Newton's power. So students, we had seen that we had started our derivation with the momentum, that is FAB dP upon dt dP and dPA upon dt dPB upon dt, and after that, since external forces is 0, we had considered dPA plus dPB is equal to 0, and from here we had calculated FBA plus FB is equal to 0, and from this we have calculated action is equal to minus. Means from here you can say that, okay, as there was the question, so that Newton's third law of motion is, so you can say that Newton's third law of motion is came from Newton's second law of motion, that is rate of change of moment. Okay students, so that's all for today. Tomorrow we will discuss one small numerical based on the conservation of momentum, and after that we will discuss equilibrium of particles, Lamè's theorem and free body diagram in the next video. Thank you students. Have a nice day. Take care.